Okay, so we are still discussing the input-output aspects of the operating systems. We talked about the hardware aspects, and we are going to start talking about the software side of it, which is more interesting for us actually. But without knowing some detail, some hardware detail, it doesn't much make sense to talk about the software that runs on the hardware. So these are some of the issues that comes up with the operating system input-output software. If you are designing software for the input-output systems, for the operating systems, your software should be device independent. What does that mean, device independency? Your software should be able to, I mean, at the end, you should be able to write programs without paying any attention to the where you are creating your files, for example. It doesn't matter if your file is on a hard disk, or on a SSD drive, or on a maybe CD-ROM. It doesn't matter. Your program runs the same way. It is written the same way. So this is called device independence. Okay. So any program can access any I/O device without having to specify the device in advance. You don't care where the device is, what the device is. You just open your file. That's one example. So that's device independence. Okay. The other one is uniform naming, very similar to device independence. Uniform naming. The name of the file should be standard. It should not depend what the medium is, hard disk or floppy disk or network drive or cloud drive. It doesn't matter. It should be named the same way. I mean, hard disk files should be named maybe like using a fixed format, or cloud files should be named with a different format. This should not happen in any operating system. So the software should provide this capability for you. Another thing is error handling. All the software, all the I/O software of the operating system, they should handle the errors in a similar way. Okay. What do I mean by in a similar way? Error should be recovered as at a very low level. Okay. For example, if you are reading a file from a hard disk, if there is a problem with the hard disk, you could not read the file, the hard disk device controller should handle the error first. If it cannot handle it, then your device controller should handle it. Otherwise, your operating system should handle it. Only if none of the lower levels can handle it, your user level software should come into the play and handle the error. What can you do with the error handling, for example? Let's say you are reading a file, and when you read the block, when you read the sector, you realize that one of the bits are wrong because checksum didn't verify the file that you have read. So what you are going to do, you can try reading the file again as a controller. You can try reading the sector again, because sometimes even a small dust particle can prevent a file from being read correctly. So if you read it again, sometimes these problems go away, because these are mechanical devices. If you do it again, it might work. So this kind of error handling. If it doesn't work, then you need to report it to the driver. Maybe the driver would know that it's a bad sector and it needs to relocate the sector, and etc. So this is the behavior of the error handling with the I/O software. What else? There is this synchronous and asynchronous transfer issue. Synchronous means blocking. What do I mean by blocking? When you start your I/O as a process, since I/O is so slow, you just block, right? You just block and go to sleep. Your process goes to sleep until it gets an interrupt that says that your I/O is complete, right? So that's a blocking. Blocking I/O, and however, most of the physical I/O is asynchronous. That means that you, the data is being read from the hard drive or from the network drive or from the mouse or wherever. Okay, CPU starts the transfer and goes off to the something until there is an interrupt, and but this takes some CPU time really. I mean, every time something happens, you get interrupted. It takes very much CPU time. So synchronous blocking I/O transfer is more efficient, but sometimes in order to make things more faster, not for the CPU, but for the overall performance, because as soon as something happens, you want to know it. Okay, as soon as something you want to know it, you don't want to be blocked. You always active. You are sitting in a very tight wait loop. This wastes some CPU time, but performance-wise it is much better. So if your CPU doesn't have anything to do, then maybe you can use technique asynchronous interrupt-driven I/O. Okay, and there is this buffering issue. The speed of the I/O device and your speed of the CPU doesn't match. CPU is much faster most of the time. When you are reading from the hard disk, or when you are reading from the network, or when you are reading from the mouse, data comes in or written to in a very slow way. So you need to buffer your input or output someplace so that CPU can write to the buffer and go to do something else, and your I/O device can use that information from that buffer and continue doing its work. This is called buffer. And sometimes you need to buffer the same data more than once. There might be a buffer inside the device itself, or the device controller. There might be a buffer on the device driver. There might be a buffer on the software itself. So the same thing might be buffered more than once, and this is another issue. So we will look at each of these one by one. And more details will come about the software. Any questions? Forgot to give you the attendance sheet. Adette senden başlayayım, şey çizimleyeyim. Ama tarihler aslan gelir. Bu kızın hakkında nasıl ödeyeceğiz ya? Okay. So let's go look at some other issues with the I/O software. One is the I/O type. There are three different types of I/O types. One is programmed I/O. The other one is interrupt driven. And the last one is DMA. So actually we looked at the DMA and the interrupt-driven I/O in some detail, and we will come to see some other details. But this is programmed I/O. Programmed I/O is the simplest one, and for some cases it is the most straightforward to implement, and sometimes it is done that way. So this is your kernel space, and this is your user space. Let's say you are going to print these letters to this printer. Okay, this is your printer. Okay, so what you do is you copy these letters, which is in user space. These are your string. Okay, to your input output routine, which is in the kernel space. Kernel space is going to do it. Okay, so you copy them here, and there is a process running that does this printing job. This process takes one of the letters, the first letter, this one. Okay, just takes this one, and it writes this letter to the appropriate register of the I/O device controller. Okay, I/O device controller has registers. Remember, they have registers. It writes that letter to that register, and it waits until the I/O device is ready to be written again. Okay, so the CPU is sitting in a very tight loop. It is waiting for printer to be ready for the next character. When the printer is ready, then the second letter is printed, and then the third letter is printed, and it goes that way. So your CPU is doing the whole thing in a different process. Your CPU is doing the whole thing, and while it is doing it, it is waiting always. It is always waiting for the I/O device to be ready. If it is not ready, then it will wait. So this is the main SATA code or C code for this kind of I/O in the kernel space. Okay, using the programmed I/O. So at the beginning, you copy the buffer from the user space to my buffer. This is from user space, and this is my buffer. Okay, and this is the number of elements, the number of characters that I am going to print. Okay, so from 0 to count. So this loop is for waiting for the printer to be ready. So it says that printer status register. Okay, it is a register. Okay. So C is a pointer. When you take the reference, it becomes a memory location, and I guess it's a boolean. Okay. If it is not ready, then I will wait. You should be. I mean, this is not a good way to put that semicolon here, but they did it that way. Okay. So you should wait until the printer is ready, and when the printer is ready, we do this printer data register PI. Okay. So that's it. And then when we are done, we are going back to the user, saying that okay, your printf works that way. Okay, printf kind of works that way if it is implemented using the programmed I/O. So what kind of space does the system implement? Does it use I/O memory mapped I/O or I/O port space? Remember, we had two types of I/O communication. One is the memory mapped I/O, the other one was the port space. Which one does it use? I/O mapped or memory mapped or I/O port space? It is, yes, it is memory mapped, because remember how was the memory map like? At the end of the memory or beginning of the memory, doesn't matter, it depends on the architecture. At the end of the memory, there are special memory fields, which are not memories actually, which are the communication mechanisms for the I/O devices. So maybe this one is this pointer. Okay, this pointer is pointing to that space, and maybe this pointer is pointing to that space. But these are not memory location, these are connected to the I/O device. Okay, so whatever you write to that location is printed on the paper. Okay, for this location you are not writing anything, you are reading from that location. When you read from that location, it tells you that if the printer is ready or not. Okay, so this is memory mapped I/O. Since it's a memory mapped I/O, I can use my regular C expressions, pointer expressions, to communicate with the printer. Okay, to communicate with the printer. So programmed I/O is something good, very simple. We can implement it all the time. But there is a problem with this. What is the problem? Very serious problem, and that's why it is not implemented much. Busy waiting. What?
Busy waiting. Yeah.
There is a busy waiting. Yes, there is a busy waiting here. It waits. It wastes the CPU time by waiting until the printer is ready, and the printer is very slow. I mean, it might take let's say 10 milliseconds to write a character. So the CPU is much faster than that. Maybe it's going to do this loop maybe tens of thousands of times, maybe millions of times before each character is printed. And we are not using that CPU time for something useful. So what would be the solution? The solution would be the interrupts. Okay, but this is a good example for using memory mapped I/O. So programmed I/O takes CPU time. If each character takes 10 milliseconds, after each character is written to the printer's data register, CPU will sit in an idle loop for 10 milliseconds. Wasted time, enough time for context switch. I can context switch, do some other work, and come back. And for this one, we said that we should use interrupts. How are we going to use interrupts? Instead of going to into a busy wait loop. We are going to go to sleep, and when the character is printed, the controller device will issue an interrupt. It will wake me up. Then I will write the second character. Then each time each time I wake up, I write another character. So this is called interrupt-driven I/O. Okay, so this is the code executed. Okay, this is the code executed at the time the print system call is made. Okay, when I make a print system call, this code is executed, and this code is executed when interrupt service procedure is run, whenever I wake up from the interrupt. So let's look at the initial one. As I said, it starts as before with the programmed I/O. I copy from the user space to the kernel space this many bytes. Okay, I do that. Then I enable the interrupts because I need those interrupts. Okay. Then I wait the printer status because somebody else might be using the printer, so I need to wait for that. There is a busy loop. I can set up another interrupt for this one, but we are going to go. We will not go into that detail. And we say that if the printer status is ready, then I can write my first character. Then I go to the schedule. I say to the scheduler that I am going to sleep until I wake up. Okay, until there is an interrupt. I am going to sleep until there is an interrupt. So this is the initial part. Okay, this is initial. When I say printf printf A, B, C, D, okay, something like this happens, okay. So it goes there, it enables the interrupt, and as soon as it prints the first character, okay, let's say you are writing to the printer, as soon as it prints the first character, it goes to sleep. Okay, when the first character is printed, an interrupt is issued, and I come back and I'm running this routine now, interrupt pending routine. If the count is 0, then I am done. Okay, if the count is 0, then what does that mean? If the count is 0, then I unblock the user so that the user can continue. The user would know that the characters are printed. Otherwise, where is my I? Oh, okay. So I should be something. Okay, the index I should be somewhere 0. They didn't write it. We initialized count, but we didn't initialize this count. What?
Yine bir olarak inişlememiz gerekmiyor mu? Sıfırıncının inişler kısmında bastırdık.
Yeah, maybe after doing this, maybe it should be something like I++ C. Okay, so it should be initialized somewhere, and it should start from 1 in this routine. So if the count is 0, as a kernel routine, I am waking up the user. Otherwise, I am printing the next character in line to the printer, decrementing the count by 1 and incrementing the I by 1. And I say that after doing that, I say that okay, I handle the interrupt, and now I can return from the interrupt. Why is this necessary? Acknowledging the interrupt. What does that mean, interrupt, acknowledging the interrupt? You acknowledge the interrupt to who? Not the user, right? The user doesn't know if there's an interrupt is happening. The user is sleeping, and I would wake up the user from this function. How about this acknowledge interrupt? Who am I acknowledging? I am acknowledging the interrupt controller, right? Because interrupt controller told me that there is an interrupt. Okay, I'm handling that interrupt. I said that okay, I am handling that interrupt now. Okay, you can consider that interrupt handled. If there are any other interrupts waiting to be handled, now you can deal with them. That's the message. So you are sending this message to the interrupt controller. Okay, then you return from the interrupt, so the CPU can do its whatever it is doing. Okay, and interrupt-driven I/O is much better than the other one because the other one was waiting in a busy wait loop. This one, for printing each character, it doesn't wait. It prints and it goes to, it turns from the interrupt. And CPU can do the context switch and continue its job. Okay. So interrupt-driven I/O is good, but there is something, there is a problem with this kind of approach. What is the, so maybe small hint. What happens here? I cannot. Okay. When I say return from interrupt, what does it? What does the operating system do?
Context.
It context switches, right? What do you mean? It switches from the kernel mode to the user mode, and it schedules one of the processes waiting to be one of the processes in the ready state, and that process starts running. And context switch something. It is something expensive, right? Context switch is not cheap. It is better than doing a busy loop, but it is still expensive because you need to save lots of data, lots of registers. Sometimes you need to set up your memory management unit, your TLB buffers, etc. So context switch is expensive. So obvious disadvantages for interrupt-driven I/O is that interrupt occurs on every character. Okay, and interrupts take time. They are not very easy. So this scheme wastes a certain amount of CPU time, and the solution is using the DMA. So the idea is, don't use the CPU time to transfer characters from the kernel buffer to the device controller. Use the DMA device, DMA controller. We talked about the DMA, and these are the motivations for the DMA.